Before we take an extended look at the structure and naming conventions of organic molecules, we're going to take a look at the chemical, specifically the molecular polarity of hydrocarbon molecules, which, as you'll recall from the previous video, are elements that contain only carbon atoms and hydrogen atoms bonded to each other like this. Now, for those that remember their molecular polarity conventions, you will recognize that all three of these molecules are examples of nonpolar molecules because neither side, the left side, the right side, the top or the bottom of any of these molecules have more positive charge or negative charge than the other side. And one giveaway, so to speak, is the fact that you can kind of draw a line of symmetry between each of the molecules like this. Now, not all symmetrical molecules or molecules that appear symmetrical are always going to be nonpolar, so we can do a little bit of a review about how to determine polar or nonpolar. Now, the first piece of information that we need to learn in order to determine that these molecules are nonpolar are what we call the electronegativity constants, which we can find on a periodic table. For example, we can see that carbon's electronegativity constant is 2.6, while hydrogen's is 2.2. Eventually, when you've done this enough, you will commit those two numbers to memory, whether you want to or not. Now, electronegativity is simply a measurement of how well an element is able to attract electrons and hold onto its own electrons and prevent other elements from taking them. So this means because hydrogen has a higher electronegativity constant, it is going to be pulling the two electrons in this bond away from hydrogen to carbon like this. And this symbol here, don't be scared of the word vector. The word vector in physics simply represents the direction of something. So the arrow is pointing this way, which is showing that the electrons in this bond are moving away from hydrogen towards carbon because of its higher electronegativity value. Now, how much are they moving? Well, the answer is actually not very significantly, which we can find by looking at the difference in electronegativity between carbon and hydrogen, and we can see if we do 2.6 minus 2.2 that this comes to 0.4. This number is not particularly large because any molecule that has an electronegativity difference between two elements of less than 0.5 is generally considered to be a nonpolar molecule because it doesn't have a strongly electronegative atom to pull the electrons away from one atom to the next atom, therefore creating a positive pole or a negative pole. The problem is that there are more than just one hydrogen and one carbon, which means we actually need to look at the larger structures of each molecule. Now, the first thing that we can look for is the distribution of lone pair electrons, which, if you'll remember from an element like oxygen, for example, are electrons that exist in the pair that belong only to one element and aren't shared with each other the way that they are in a bond. Now, if you consider carbon and hydrogen and think that looking for lone pairs is a waste of time, you would be right, and we can see that in the Lewis structures of each atom. We can see that carbon and hydrogen only contain unpaired electrons that they use to form covalent bonds. This means that carbon and hydrogen have no lone pairs, meaning that there isn't a large cluster of electrons around one atom, and meaning, unlike an element like oxygen, there isn't a high distribution of negative charge in any of these molecules. Now, the last characteristic we need to look for is whether the dipole vectors, the movement of electrons from one atom to another atom, cancel or whether they form an overall direction. Now, how do we look at that? Well, the easiest is actually to look at this triple bonded molecule here, because if we draw the vector representing electron movement, we can see that the electrons move this way towards carbon, but on the other side of the molecule, we can see that they would move this way in the opposite direction. Now, when the electrons move in this way, are all these electrons going to want to stay together in the middle of the molecule? Well, that would be no, because the negative charge is going to repel each other. So what we see whenever we have two dipole vectors that have the same magnitude, meaning the difference in electronegativity is the same, which it would be because these are both carbon and hydrogen bonded, but are moving in the opposite direction. The movement one way is directly counteracted or canceled by movement in the other direction like this. What this means is that the electrons in these bonds are not moving towards the right half or the left half of this molecule, meaning that this molecule, neither the left side, the right side, the top, or the bottom, has more negative or positive charge than the other, and that leads us to conclude that this molecule is nonpolar. Now, if we do this with the other two molecules, if we draw in the vectors showing electron movement, we can see that the middle of these two vectors would be right here. This is right in the middle between these two, but if we draw the middle point between these two electron movement vectors, we can see that it's here, and these two, again, same magnitude, same difference in electronegativity, but opposite direction, so these two would cancel, and neither side of this molecule has more positive or negative charge than the other, and we can see that this is true with our simplest example of an organic molecule, CH4, because there is the middle and there is the middle, and we can see these are same magnitude, opposite direction, meaning that they cancel. Now, this gets a little bit overwhelming when looking at large organic molecules such as C10H22, but we need to remember that these are still made of only carbon and hydrogen, and neither carbon or hydrogen is an element with a particularly high electronegativity the way that oxygen is, meaning that neither carbon nor hydrogen is able to attract electrons and hold them in a specific location, meaning that because there is no strongly electronegative element within this molecule, there is no location where a large amount of negative charge is able to build up, and therefore this is also an example of a nonpolar molecule. The final talk that we're going to have is discussing the forces that exist between nonpolar hydrocarbons. Now, because CH4 is the simplest molecule, we're going to be looking at this molecule, and we'll explain why I haven't actually drawn the bonds for each of these molecules in. Now, because neither carbon nor hydrogen has a particularly large electronegativity, there is no location in this molecule where electrons will want to move naturally, meaning that all of the electrons that we find within the bonds of each of these molecules can move relatively freely throughout the molecule. Now, there are 1, 2, 3, 4 bonds, 2 electrons per bond, meaning that there are a total of 8 electrons that I haven't drawn in. Now, let's say for the sake of argument, 1, 2, 3, 4, 5, 6, 7, 8. Let's say that the 8 electrons are all here, which is clearly on the left-hand side of this molecule. Now, are these electrons all going to stay on the left-hand side of this molecule? Well, the answer is of course not, because all electrons are negatively charged, and they are going to perpetually be pushing away from each other because of the repulsive force of the same charge. However, at this instant in time, the random distribution or random dispersion of electrons has landed them all on the left side of this molecule, which gives the left side more negative charge than the right side, because there is an overall movement of negative charge this way giving this side a partial negative charge, and because the electrons are moving away from the right-hand side, this gives the right-hand side a partial positive charge. Now, if these two molecules were directly next to each other, all 8 of the electrons on this molecule, 1, 2, 3, 4, 5, 6, 7, 8, will also want to be on the left-hand side of this molecule, because unlike identical charges that repel, opposite charges attract to each other like this, and we have an intermolecular attraction, an attraction that exists between the two molecules. Now, the problem is these electrons, we know, are not going to stay in the same location forever, which means, is this attraction between the two going to be permanent? Well, if these electrons move away, this partial negative charge is now gone, which means this attraction will also disappear, making this attraction temporary, entirely based on the random distribution of electrons within the molecule. Now, because this intermolecular attraction is temporary, that makes it relatively weak. And this type of temporary intermolecular attraction goes by many names. You may have heard of these referred to as London forces, and if you're a biology student, you might have heard them called van der Waals attractions, although I prefer the more technical name, which are what we call dispersion forces. In fact, the term London dispersion forces is often used. Dispersion is a word that means to randomly scatter, referring to the random distribution of electrons and this temporary interaction that forms. And this, because of the fact that nonpolar molecules do not have a permanent negative side and a permanent positive side, this is the only type of interaction that pure hydrocarbons can make. In the next video, we're going to be looking at the naming and structural drawing conventions that we use to represent the simplest organic compounds, that being the hydrocarbons.